Welcome to section 4.4. It is the first part of Unit 4B. We'll be talking about the periodic table basics. Following that, we will talk about all the hidden information that the periodic table can give us, and then we'll be connecting the entire chapter back to light. We're going to start off with a little bit of history with the periodic table. There were many famous scientists that were part of the process of organizing the elements as they became known from the early 1800s onwards. But there are two gentlemen that are given most of the credit. The first one is Dmitri Mendeleev, and he was around the mid-1800s, and he designed the first periodic table based on atomic mass. And basically what happened was around his time, I think there were about 60 elements known, and he put any information he had of those elements on cards, pieces of paper. He was shuffling them around, trying to find patterns, and eventually he realized that if he based it on atomic mass, most of the elements showed patterns and properties that repeated across rows and had similarities down the columns. There were holes in his table, as you will see in the picture in the next slide, where elements hadn't been discovered at that time, and he kind of predicted that this element would exist one day with these particular properties and so forth. And of course there were some areas where they needed to be tweaking, but this table lasted for probably a good 20 years or so before another table came into existence. This is a copy of Mendeleev's periodic table, and you can see it looks drastically different than our table today, and you can also see that there are some blanks around there. In around 1910, there was another scientist that came about. His name was Henry Moseley. He's actually given credit to the modern periodic table, and he took a look at the inconsistencies of Mendeleev's table and the fact that at his time the proton, electron, and neutron had been discovered. At Mendeleev's time, he had no idea that there were subatomic particles. So in 1910, the use of the proton became the focus of the periodic table. And what Moseley basically discovered was if he rearranged the table based on atomic number rather than atomic mass, the inconsistencies of Mendeleev's table were fixed. And so that's what we have today, a periodic table that goes in order of increasing atomic number. It's based on the proton number of the element. And modern periodic law says that elements in columns have similar properties. So let's discuss the organization of the periodic table. We have two directions on the periodic table. We have columns, which are running vertical north-south. They are also known as groups or families, and you can see that right here. And then we have periods. Periods run east-west. They are our rows of the periodic table. Notice that there are 7 periods, and there are 18 groups or families. We'll find that the groups of the families are labeled with a number letter designation, and we've already talked about these number letters. In the side columns, which we have been calling the towers, that Roman numeral and the letter helps us designate the charge. We know that this is column 7A. We know that if we subtract 7 from 8, we'll get a charge of -1, and we can do that going backwards. We also know if I go over to the metals, the column number is the charge of the metal. And then the other thing that we learned in the last unit is that the group number itself is also the valence number. So I've got 1 valence electron. Here I have 2, 3, 4, 5, 6, 7, and the last group has 8 valence electrons. Of course, helium only has 2. That's an exception. So that information is important. We're also going to learn that the A designates that it is a representative element. And if we look down here, you can see the B's. The B's are going to represent transition elements. And I also want to point out that the number has nothing to do with the charge nor the valence electron in the group B block. It's only the representative elements that we can use that information for that purpose. Each element has a specific set of information. This should be a lot of review for you. Of course, the whole number on the periodic table is going to be the atomic number, which tells us the number of protons in the atom. We've got the average atomic mass, which is the weighted average of all the naturally occurring isotopes. We learned how to calculate that in the last section, and it will be in decimal form. And we want to also remember that its unit is AMUs. And if we talk about 1 mole of atoms, we then can say that, say, 1 mole of carbon atoms, which is 6 billion trillion carbon atoms, would be equal to 12.01 grams. We've got, of course, the element symbol and the name. Other information can be put on the table, but these are just the 4 basic informational pieces that you usually find. When you looked at the periodic table, you noticed that there were 2 rows down at the bottom. These are called the inner transition elements. And before a gentleman named Glenn Seaborg moved these 2 rows down, they used to belong to the main portion of the table, and in the next slide you'll see what that looks like. These are the elements that are more recently found. They're kind of rare. They're radioactive. They don't have a lot of function in our society. So Glenn Seaborg decided that he should move them down underneath the table, and he did that despite his counterparts' beliefs that that would be a crucial mistake for him in his career, and it turned out that it was a wonderful thing for his career. Here's a picture of the inner transition metals inside the main table. You can see here that you really would need 2 pieces of paper to actually put the periodic table together now. It's a little cumbersome to use, and they wanted the periodic table to be something very handy. And so that's one of the other reasons why those elements sit below the periodic table. We can divide the periodic table into 3 types of elements. Remember, at the beginning of the year, we took a colored marker, we went down our periodic table, and we made a staircase line. That staircase line was important because it separated our metals from our nonmetals. Notice that hydrogen really is a nonmetal. It's kind of misplaced. And then the other thing we want to remember is that this element right here is aluminum. It is a full-fledged metal. Anything that sits on the border of the staircase line, with the exception of aluminum, is considered a metalloid or a semi-metal. This guy right here, some periodic tables say it's a metalloid and some say it's not. Since it's one of those very rare elements, we don't worry about it too much. Some properties of metals could be that they are all solid at room temperature, except for mercury. Mercury is the only liquid metal at room temperature. All metals have formability, which means that they have the ability to be malleable. They can be flattened into thin sheets. You can look at aluminum foil for an example of malleability, and ductile, which means it can be drawn into wire form. And you can see with this picture, copper is in wire form over here. Metals are great conductors of heat and electricity. There's a picture of a pot down here. Aluminum heats up extremely well. Remember, it has a very low specific heat, and so it can heat up, thus heating up the water and cooking your food a little bit faster. Metals are shiny. They have high luster, and you can see that obviously with any of these pictures, especially gold up here. Wouldn't you like to have that much? And then the last thing is that metals have very high strength. Metals are usually our building materials. They last and are very durable. The prefix non means not, and so our properties of nonmetals will probably be most of the opposites of metals. When in states of matter, most of the nonmetals are gases. There's just a few solids, and there's that one liquid at room temperature, and that happens to be bromine. They have very poor formability. Take a look at this picture of sulfur. If we tried to flatten that, it would just crumble. And so we find that there isn't really any malleability or ductility to nonmetals, and they are very brittle. Of course, they are opposite of shiny. High luster means low luster or dull in nature, and they are poor conductors of heat and electricity. And then you have your metalloids. Your metalloids are all solids, also known as semimetals. They share properties of both metals and nonmetals. They can be semiconductors of electricity, meaning sometimes they are good conductors and sometimes they're not. And two of the most probably popular semiconductors are silicon and germanium.